Okay, so I strongly recommend you to pay attention to the merge sort and quicksort implementation. Okay, so with the quicksort, as I said earlier, you first find a pivot, and then based on that pivot, you arrange the elements of the array such that left part of the pivot is smaller than the pivot, and however the right side of the pivot is going to be greater than or larger than the pivot. So the quicksort method is going to be, run with the given array, and then you give the first and last indices of the portion that you would like to sort. And based on that, if first is less than last, so if you have more than one element to sort from, then what you're going to do, you get the pivot element as to be the first element of the array. So this is, again, implementation dependent. You can choose a pivot that is the last element, that's the medium element, or that is the second element. It's up to you. So it's up to the designer, the programmer, to choose whatever pivot he or she wants to choose from. And then you choose the first element to be the pivot, which you're going to arrange your entries in the array. Then you partition your array such that you're going to generate the new settings for the pivot, wherever it is going to be in the final set, and then the remaining elements arranged according to the pivot. So this is going to give you the split point, partition E pivot element first and last. So basically this partition method is going to be given the array, and then the first and last entry, and then the pivot element. So I'd like to rearrange things in this array such that my pivot element is going to be in its final position, and it is going to have the first and last indices given with these arguments. And at the same time, this method is going to return you an integer value which indicates where this pivot element is going to be in the final case. So let's say I have 9 in the previous example I shown you. Let's say 9 was the pivot, and then this is where it is going to be, and this is position 4. Then this is going to return you the split point to be as the 4 in the final case. And then you'll use this to do the quicksort in a recursive fashion. As you see, you call the quicksort for the left part E, and then the first and split point -1. So it's going to basically be the pivot element. The new pivot element of this part is going to be the first element. You'll start with the first location, and then you'll go into the split point -1. That's why it says from first, this is the pivot element, and then you're going to start from the first element to the split point -1. They forgot actually, they forgot the, no, actually no, that's true. That's the indices, the quicksort is called with the array and the first and last indices. So you call with the first element and then split point -1. And the remaining part, for this part, you use split point +1 as the starting point, and then you go all the way to the last entry, right? So you basically, again, you will use this as the pivot for this part. It will go in here, let's say, and then you call the same thing for this part and this part in a separate recursive call. So let me show you an example to implement here, and you will have a better idea. So let's say you are given this let me pull it up a little bit. So if you look into this, now it's good. So if you look into this, this is how the partition algorithm works. Okay, basically what you do is that you keep track of two indices. So originally my pivot is going to be the first element. So this is my pivot. And then what do? I have two indices which shows me the number that is bigger than the pivot. Too big index. And then I have a too small index. So what do? I go in each direction to find the element, the first element that is bigger than the pivot, bigger than 6. So I start. Is 2 smaller, bigger than 6? No. I increment my index to be to the next position. Is 8 bigger than 6? Yes. So I found that this is supposed to be on the left of my pivot element. So what am I going to do? I will find the smallest, first smallest element and swap it with this big element. So I go here as well until I find a small element, then the pivot. So I compare with 6. Is 6 less than, is 6 greater than 14? No. So I'll update my too small index. Is 16 smaller than 6? No. Is 11 less than 6? No. And then you compare with 4. Since 4 is less than 6, you will do the swap. Now what you are going to do is that this is going to be 4 and this is going to be 8. Okay? And then I continue. Now my new value points to 5. Is 5 less than 6? Yes. So I advance one more. Is 10 greater than 6? Yes. So I will need to swap this as well. And then I will update my new value. So it will point to this one. Since 13 is greater, it needs to be on the right hand side of the pivot. I continue. 3, I check. This is again needed to be swapped because I will rearrange things according to 6 so that bigger elements will be on the right hand side, smaller elements will be on the left hand side. So I will swap 10 and 3. Now this is 3 and this is 10. Okay? And then I continue with my index to be incremented by 1 to point to 9. 9 is greater than 6, so that's correct. It's again needed to be swapped if I find something similar, something smaller. So I will go into the next index. This is still bigger, so I will continue. I will come 15. This is bigger. I will come to 1. This is smaller, so it needs to be before 6. What do? I swap it with 9. So this becomes 1 and this becomes 9. And then I continue to update this to be 12. Since it is greater than 6, I will, leave it there. I will advance one more position, right, until, no, it will remain there since it's bigger. And then for 9, I will check it's bigger. I will go try to find a smaller element. Is there a smaller element? I will compare with 12. No, I will go one more. And this will indicate me when I need to stop. Since I have already searched everything, I know that, since this is now, this index is, let's say this is J, this is I is bigger than J, I need to stop it because I exhausted all the searches. And this exactly indicates where I need to put 6 in. If you look into the right hand side, all the elements on the right hand side of 6 are greater than 6. So you see 12, 9, 15, 7, 10, 13, 8, 11, 16, 14. All of them are bigger because I did swap the ones that are smaller with the big ones here. So basically what you do, the last swap is going to be with the pivot. So you swap pivot with 1, which is going to basically make this to be, 1, and this becomes 6. So if you look into this new thing, you see that this is your pivot. On the left hand side, everything is smaller. On the right hand side, everything is bigger. Okay? So the algorithm, I will explain it again on a different example too, but just wanted to show you on this real, example how the partition works. This is partition part of the algorithm. So if you go into the implementation, again, let me show it here. So let's say you are given this set of integers. We again do the same implementation. We select as our pivot 40. So this is going to be the pivot. And I will have a 2 big index and then 2 small index that are going to be checking for bigger and smaller elements as opposed to my pivot element. So you have the 2 big index to start with initially on the first element. So since it's smaller, you continue to check the next element. And then since this is smaller, you continue to check since this is bigger than 40, you found an element that needs to be swapped if there's a smaller item on the right hand side. And then once you find it, you stop there and you start for the too small index to reduce. So you decrement, since this is bigger, you go to the next element, which is 30, and then when you compare 30 with 40, you see that this is smaller than, so you can swap these two entries. So you basically swap these two and then get it in such a way that so far this part of the array is smaller than 40, this part of the array is greater than 40. Okay? As you go, you make the inner portion smaller and smaller, such that at the end you find the pivot point where it needs to stay in. And then the next thing is you continue with the same thing. You find the big element that is going to be swapped next. So when you continue, you get 60. As you see, 60 is going to be on the right hand side if you have a smaller element. So you go into the too small index, you found a 7, which needs to be on the left hand side of this thing. And you will swap these two, which is going to give you this part smaller, this part larger. So once you do the swap, as you see, you have come so far with this part smaller than 40 and this part greater than 40 at the end. And if you continue in this fashion, you see that you advance the too big index, which is going to stay there because you find 50 as a bigger element. And then you go and try to find a small index. You will continue until you find a small index. However, the one that you have found, the small index, is already indicating that you are done with the search because it is now smaller than the too big index. So you must have checked all the elements so far. This indicates that you have checked all the elements so far. So now you know that your too small index points to where your pivot element is going to go into. So the last step of the procedure is to swap these two elements and to get the 40 into its final position. So the last thing that you do is you'll swap these two, so the pivot index is going to be 40, right? Next thing what you're going to do, you will call this part and the pivot is going to be 7. And then you'll call this part and then your pivot is going to be 50. Okay? Any question? So if you look into the final form of this thing, as you see, the elements that are on the left hand side are smaller than the pivot, and on the right hand side are bigger than the pivot element we have. Then you recursively call the same algorithm over and over to get it into the final case. So what is the best running time of this algorithm in terms of n? As we mentioned in the first lecture, we said that you have more than you need to perform more comparisons as opposed to the merge sort. What was the reason for that? Because Quicksort doesn't always divide it into equal sizes. So the best case is going to happen when Quicksort is going to be able to divide things into equal sizes every time. So basically pivot is going to be in the middle and everything is going to be left and right in equal sizes. In that case, what would be the best case? So you will have n log n, because log n steps in each divided. So you have the Quicksort. Every time if you can divide it into two equal halves, you'll get log n steps. Log n and then n log n. What is the worst case? How could you get a worst case in the first place? How can you get that? Why? So if your pivot element is always the smallest and it is at the beginning of the array, so that means basically if your array is already sorted, you'll get the worst case actually, and which is in every iteration you will have a size of n the next time if it is sorted, you'll get n minus 1, n minus 2 size. So you'll get smaller, but it is going to be in the order of n's. So basically you'll have n minus 1, n minus 2, and then all the way to 1, which is going to be obviously O(n) square. So that's going to be the worst case. Again, this is because of the fact that pivot could be at the beginning. For the worst case, as I said earlier, if you have a sorted, so this is the same thing, depth of the recursion 3, and in each iteration you have O(n), which gives you n log n. The worst case, if you have an array that's already sorted and then you select this pivot as to be the pivot, so you'll basically get this in its place, and then you'll have 2 big index remaining here, and then your 2 small index is going to move what? How is this going to behave? So 2 big index will remain here, and then every time you'll decrement your 2 small index. It will come all the way to the first entry, and then that's where it's going to stop, right? So it will basically call the sort again for this part, which is going to have this as the pivot, and then it will have this index coming all the way to here, and then it will call this part as the new quicksort with the new pivot with 10. So every time it's going to basically decrease only one element with every sort, which is basically as if no recursion or no divide and conquer technique has been applied. So basically, in that case, you'll get an O(n) square implementation, and so it's going to basically be not really helpful to implement using quicksort. So that's to prevent that. Any idea to prevent such behavior? I'm just going to show you the final thing. So everything is greater than here. You'll call the quicksort with that part. So how can I prevent this problem? This pivot dividing the whole thing not into equal or close to equal sizes. The main reason for this is what? What's the reason? What's the reason I'm dividing this not into equal or close to equal parts every time in this case? Because of what? Because of the pivot selection, right? Because I'm selecting the pivot as the minimum value every time, it basically cannot divide it into possibly equally sizes. It just eliminates one element every time, since I'm selecting the smallest element every time, which is the first pivot. So to get rid of this behavior, they have tried several heuristics, and basically they use for selecting the pivot as the median of the 3 elements. So the first element in the array, the last one, and the medium one. So they select whichever is the median, whichever is the medium of all 3 elements. They select this as the pivot element. Okay, so that's a heuristic that they have generated to optimize the behavior of the quicksort. Okay, so this way you'll break this pivot problem, and then at least get a better performance out of the quicksort implementation. So on the average, however, ignoring the fact that in the worst case it could go O(n) square, in the average it goes O(n) log n, and in mathematical terms it has been proved, but we are not going to go into that direction at all. So this has been already sent to you via email, so you should have the material with the link in your emails. Okay. However, if there's any problem, please let me know again. So a quicksort example. Again, let's do this quicksort together. So if you remember, we start with as our pivot as 15, right? So my pivot is going to be this value. And then I will have my 2 big index here. So I'm trying to find a big element that is bigger than 15, such that I will swap with a small element that is coming from here. too small index. So is it bigger than 15? No. So I'll advance it one more. Is it bigger than? No. And then I found the bigger element that is bigger than 15, my pivot. And then every time I will try to find a smaller element compared to 15. Is the too small index pointing to a smaller element? Yes. So I will perform a swap. This will become 5, and then this will become 21. Now I will continue until these 2 points merge at some point. So I will continue with this one. Is this bigger compared to the pivot? Yes, it is bigger. So I'm going to basically find a small element that I can compare with and swap with this element. So is this smaller? No. Is this smaller? No. I will again decrement my pointer by 1. And I found the smaller element. So I'll just do the swap. So 8 comes here, and then 25 comes there. So I will go on to trying to find a bigger element. Is this bigger? No. Is this bigger? No. And then, is this bigger? Yes. The new value is 25, right? So it's bigger than my pivot 15. And then I will try to find a smaller element, and I will update my index to point to this. However, this will indicate that I and j is, this one is already bigger than this value. So I have finished all the options and I'm done, which means if I put my pivot here, I will see that right hand side is all bigger elements, left hand side is all smaller elements. So basically I'll do the swap with this one. So this will become 15, and then this one will become 9. So that's what we get after this point. As you see, 15 is here, 3, 8, 5, 3, 12, 9, and then you have 25, 18, 28, 21. Okay? So the division here is, if you look into here, 6 elements here, and then 4 elements there. They're not equal. Obviously, that's going to cause the inefficiency of the quicksort. And then next thing, I will go with 9. This is my pivot for this part of the array. That is called the second step of the recursion. And then I will compare, is this bigger than 9? Yes. Is this smaller than 9? Yes. So I will just do a swap. This will 3. This will become 12, right? And then I will continue to find a bigger element. This is not bigger. This is not bigger. This is not bigger. And this is not bigger. So I will go all the way to the end, right? And then I will try to find a smaller element, which is going to tell me, hey, move to here, and it's going to point into the to the element, right? Smaller, that's smaller than 9, and since the pointers have already been merged there, I will say that, hey, this is where my pivot is going to go in which case I will just swap this with 9, and then this will become 8. So that's how you see 8, 3, 3, 5, and then you have 12 here, and then 9 is in its final place. This part is unsorted. This part is, has not been decided in terms of their final locations. However, 9, 15 has been, in their final positions. You'll do the same for 25. This is your pivot, and then you have the big index. This is not bigger. You'll find the biggest, this one, and then you'll find the smaller. This one is smaller, so you'll swap those two. Now this one is becoming 21, this one is becoming 28, and then next thing you'll go here, right? And then this one will come here, which tells you that you're over with the swap procedure. Now you need to just insert 25 into its final form, which goes in here, and then you have 21 swapped to here. Okay? And then the next steps is the same exact thing. You just basically need to find the location of the corresponding entry and then do the swaps and insert it into the correct location. Okay? And at the end, you have the sorted sequence as shown here, because you'll be left with, a really small number of elements which will basically go into their exact spots in the sorted sequence. So if you look into the quicksort implementation in the algorithm, it's rather interesting to have the partition implemented in Quicksort. So as you see, you have an array that is given as an input, and then you try to generate a pivot element, and also the array that is arranged based on the pivot. So pivot is going to be basically in its correct location, and then the rest of the array is going to be arranged based on the pivot that you have. And the begin, you have, this is again Pascal structure, pseudocode. You have the pivot that is set to the left, x left, the first entry of your array. And then you start with the left, and then R indicates right. While L is less than R do, so you basically check for the pointers, positions. And then while XL is less than or equal to pivot and L is less than or equal to right, you continue incrementing your pointer from, remember we started from left hand side, and then we try to find an element that is bigger than the pivot. So that's what the first while is doing. And then the second while is basically checking for the reverse. So every time it is trying to find an element that is smaller than the current pivot by indicating, this is R. Every time it subtracts 1 to go on to the next left position until you have found one. Once it is found, it's going to basically exchange XL with XR. So it will exchange those two values, that is smaller than the pivot and then the bigger than the pivot elements. Once you find and exchange that, it is going to basically set the middle to this R. This is a while loop, so it will do this over and over, starting with the first position and doing it again and again. And then once you're done, you'll find the middle point is equal to R, and this is the last step, which basically you are swapping the middle element, the pivot, with the X left. So X left is the pivot that you have. You swap it with the position, the middle position that you have found that the pivot is going to go in, and in which case it is indicated by R. If you remember, you go L comes here and then R comes there, and that's where exactly you will insert your pivot into. So once you have the partition, if you recall, this is the partition. Partition finds the correct position of the pivot, right? And then it arranges the elements according to the pivot. So if you look into the actual quicksort implementation, as you see, you have the left and right indicators for the indices for the array that you're going to sort. It first does partition X left and right, so you get the position of the pivot by calling the partition. It partitions it, and then using that partition, it basically generates the middle, sorts the first part with the same recursive call, quicksort left and middle -1, quicksort middle +1 and right. So basically it calls this part in a separate recursive call, this part in a separate recursive call after that. Okay? Any question? So if you look into the example that involves quicksort, so every time, you're going to basically have this whole big list at the beginning to quicksort, and the left is going to be set to be the first element, and then R is going to be set to the rightmost element in the array, right? And then next thing you're going to do is that you'll set this as the pivot. So this is your pivot, and then based on this, you're going to basically find an element that is bigger than 6, and then find an element that is smaller than 6. So once you find those, you'll swap, right? So this one will become 4, and then this one will become 8. And then you'll find the next bigger element, which is 10, right? And then you'll find the next smaller element, which is 3, and then you'll swap those two. So this becomes 3, and then this becomes 10. And the next thing is that you will find the next smaller element, which is the next smaller element, a bigger element, sorry. It is 9, and then you will find 1 here, so you will swap those two. This one is becoming 1, and this one becomes 9. And then the next bigger element is going to be 12, right? So this is the next one. And then you will update your pointer to be 12, since this is still not smaller. The next smaller is going to be this one. However, this indicates that you are done, and that's where exactly your 6 is going to go into, and then that's why you have 6 here. Okay? So now this partition is being finished. So you call the partition. Partition returned you the new array with this setup, and then the pivot in between. Now you will call recursively for this part to sort, and that part sort. As you see, this is the pivot. However, since it is the smallest element, obviously it will remain in its current position, since you don't have anything that is smaller on this side to swap. And then similarly, you will call for this part in a recursive fashion the quicksort. And when you call this part with the quicksort, since again it's smaller, it will remain in the same spot. When you come to this is going to do the quicksort again, right? In which case you're going to basically have 4 as your pivot, and then 5 is going to be the bigger element, and then 3 is going to be the smaller element. You'll swap these two. 3 comes here, 5 comes there, and then the next thing is you're going to update the too big. It's 5 now. Yes, it is bigger. And then you'll find the smaller. Yes, it is 3. It is smaller. But you're done with the search. So you'll basically now swap 3 with 4, and then this is going to be the final form of the thing. So you have 3, 4, and 5, and then 4 is the pivot's final position. Note that the circled ones are in their final positions. Okay, they're already in correct locations. Then next thing is that you have 3 and 5. Since they're all alone, you don't need to really do anything to those, and they're in correct locations because they are the single elements in the quicksort. And when you look into the for these, actually left and right are equal, so the loop cannot even go inside the thing to implement, since left and right is same. And for the right hand side, let's do this. If you have this as the pivot, you'll find a big element, which is 15, and then you'll find a smaller element than 12, which is 11, right? And then you'll basically swap those two. So 11 comes here, 15 goes there. And then you find the next biggest element, which is going to be 13. And then you have the small element, 8. So you'll swap those two, right? 8 comes here. 8 comes here, and then 13 comes there. And the next thing that you're going to do is basically you'll adjust your pointer to point here, and then this one is going to be pointing the smaller one. However, since the pointers have already merged, you'll just swap your pivot with 8, in which case 8 comes here, and then 12 goes there. So 12 finds its final position, and then you'll do the same thing for this part and for this part as well. And if you do this, as you see, you will finish it at the end with only one element left, which is going to finalize the solution. Any question? So if you don't understand the implementation, please go over it again, because it's important. So when you look into the recurrence relation, although it's not really, an implementation that's covered by our class, but I just wanted to show you this. Every time you have a problem of size n, you get 2 problems of size n over 2, and an additional operation that requires n different operations in the implementation. So this is called the recurrence equation, which if you write this down, you'll get O(n) log n in the average case for this implementation of the quicksort. However, again, in the worst case, if you have this kind of relationship, every time you will have Tn equals n minus 1, and then you'll every time get smaller and smaller pieces of n elements, which is going to cause you to get O(n) square at the end, which is going to be the worst case execution time for this implementation. Okay, so this PDF is also available for you to go over and see the different implementations of the sort algorithms. Any questions? I will stop here, and if you have anything that you have specific in mind, you can come and talk to me. See you.